Hello, everyone. I'm Richard Ren, a PhD student at Carnegie Mellon, and very excited to share our work, Enhanced Multi-Objective A-star using Balanced Binary Search Trees. In many applications, very often we want to plan paths while optimizing multiple objectives. For example, on the left, the robot wants to find a shorter path while minimizing the path risk. On the right, we want to plan paths to transport hazardous materials through a city while minimizing arrival time, fuel usage, and avoid those busy urban areas. With that in mind, in this work, we consider this multi-objective shortest path problem. Given a graph where each edge in the graph is associated with an m-dimensional non-negative cost vectors, the goal of the problem is to minimize the accumulated vector cost for path from the start to the goal. And since we're optimizing vector cost, or say multi-objective, in general, there does not exist a single solution path that can optimize all the objectives at the same time. We therefore seek to find a set of Pareto optimal paths. A path is Pareto optimal if we cannot improve over one objective without deteriorating at least another objective. For example, in this graph from node A to D, there are 4 feasible paths. And among them, path ABD and ACBD have Pareto optimal or say non-dominated cost vectors, which are marked as the green dot in the figure on the rightmost side of the slide. And for path ACD and ABCD, their corresponding cost vectors are dominated. Intuitively, given two vectors, A and B, if A dominates B, then A is better than B along all dimensions. The set of all Pareto optimal cost vectors form the so-called Pareto optimal front. And the fundamental challenge in this problem is very often the large number of Pareto optimal solutions. And to find them, the algorithm need to run a lot of dominance checks to compare or say to tell which cost vector is better. And to address the challenge, many approaches have been proposed in the literature. In this work, we're going to focus on algorithms that can compute the exact Pareto optimal front. The starting point is this NAMO A star, which runs A star-like search in a graph to find the Pareto optimal path. And then people propose the so-called dimensionality reduction techniques, which I will elaborate later. And the resulting NAMO A star-DR algorithm can run faster than the NAMO A star algorithm. And also know that both algorithms can handle an arbitrary number of objectives. Then very recently, people realize that if there are only two objectives, those expensive dominance checks can be expedited, and people propose BO A star. However, this technique is limited to two objectives only. And the contribution of this work is that we generalize BO A star to address an arbitrary number of objectives. And as a special case, we propose TO A star, which have better runtime complexity than EMO A star when there are only 3 objectives. Okay, let me set up a couple of technical terms at first. First, we use term label, which is a tuple of a vertex V and cost vector G to identify a partial solution path from the start to node V with cost vector G. And since there are multiple non-dominated paths from the start to any other node in the graph, we use frontier set alpha V defined at each node V to store all non-dominated labels at that node during the search. And as a special case, the frontier set as the destination is basically the solution set. As shown in this example, at node V, there are 3 non-dominated labels identified by different color. And in addition, each vertex has a consistent heuristic vector, HV, and the F vector of a label, FL, is defined to be the sum of the G vector and the H vector. And finally, the open list prioritizes labels based on their F vectors in lexicographic order. So lexicographic order means that we compare two vectors by looking at the first component. If they are the same, then we look at the second component, and so on and so forth. Lexicographic order makes sure that any pair of vectors are always comparable. Okay, now let's have a deeper look at the existing BOA star with this toy example. At the very beginning, at node V, the frontier set is empty. And now let's say we have the first label, L1. Then clearly L1 is not non-dominated by any existing label in the frontier set. So we will insert it into the frontier set. And in addition, BOA star maintains an auxiliary variable, G2min, which stores the minimum value of the second component of all the labels in the frontier set. Now it's updated to B18. Okay, now let's say we have a new label, L2. And the first key point is that among all labels that are popped from open, the first component of those cost vectors must be non-decreasing. This is because we have consistent heuristics and lexicographically sorted open list. This is the so-called dimensionality reduction technique. So in other words, now we only need to worry about the second component in those dominance checks. So in this case, 9 is less than the current G2min 18. Therefore, L2 is non-dominated. So again, we will insert this label into the frontier set and update G2min to be 9. Okay, now let's say we have a third label. And then similarly, in this case, the second component of this label, 11, is greater than G2min. Therefore, L3 is dominated and is discarded. Okay, now let's go back to the big picture. So basically, there are two key sub-problems in this multi-objective A-star-like search. The first one is the check problem. That is, given a set of non-dominated vectors B and a new vector G, we want to check whether G is dominated or not. And second is the update problem. Given a set of non-dominated vector B and a new non-dominated vector G, we want to compute the non-dominated subset of B union G. And a naive algorithm can solve this problem by using a linear time, that is a for loop over all the vectors in B for dominance checks. And as we have seen, BOA star can do this in constant time by introducing this auxiliary variable, G2min. Now the remaining question is how to generalize this technique to more than two objectives. Okay, I'm going to illustrate the idea with another toy example. In this example, we have 4 objectives. And at the very beginning, we will insert the first label into the frontier set. Okay, then instead of maintaining G2min, now we're going to generalize this to be a balanced binary search tree. In this work, AVL tree. So the first key point is, again, we don't need to worry about the first component of those vectors because of this dimensionality reduction technique. Okay, second, this tree is organized in lex order. That is, every node in the left subtree must be lex smaller than the root node, and every node in the right subtree must be lex larger than the root node. And if there are only 2 objectives, then clearly this tree degenerates to be a singleton tree, that is a tree with only the root node. And the value stored in this root node is basically G2min. Okay, now we're going to leverage this tree and traverse it recursively to check for dominance. And there are 3 cases. The first one is the base case. So if the input vector is dominated by the root, then it will be discarded. Or if the root node is empty, then the input vector is non-dominated, and it will therefore be inserted into the tree by using a regular tree insertion operation. And also note that tree rotation will be conducted when needed, which takes log n time. Okay, then the next case is if the input vector is lex smaller than the root node, then in this case, we only need to recursively traverse the left subtree and we can ignore the right subtree. The reason is that no node in the right subtree can dominate the input vector. And more detail is that the first component of vectors in the right subtree must be greater than the first component of the input vector. And this is because of the way the tree is organized. Okay, the last case is that the input vector is lex larger than the root. In this case, caveat, we have to go through both the left tree and the right subtree for comparison. As an example, in this case, the input vector 20, 13, 7 is dominated by the orange vector. However, this orange vector is in the left subtree. However, if there are only 3 objectives, we can actually do better. In this case, the second case becomes if the input vector is less larger than the root, then we only need to recursively go through the right subtree, and we can ignore the left subtree. The reason is that no node in the left subtree can dominate the input vector. And more specifically, the second component of vectors in the left subtree must be greater than the second component of the input vector because of the way we organize the tree. Okay, briefly summarize. For the check problem, if there are only 3 objectives, our approach TOA star can solve this check problem in log n time, where n is the size of the tree. And in general case, the approach still takes a linear amount of time. And similar kind of analysis can be applied to the update problem also, and I will skip that part. However, either with 3 objectives or an arbitrary number of objectives for the update problem, it takes linear time. But as we will see from the numerical results, this approach in practice still runs much faster than the baselines. Okay, for numerical evaluation, we use 3 baselines in this work. The first one is NAMO A*-DR from the literature. The second baseline is a naive extension of BOA* to handle arbitrary number of objectives. Specifically, the frontier set is represented as a list. And then the third baseline further improves the second baseline by using the Lex order to sort this frontier list. Okay, first we're testing a 10 by 10 empty grid with varying number of objectives. Those figures show the runtime of each instances, and the horizontal axis shows the number of Pareto optimal solutions for those instances. And very clearly, our approach runs much faster, like up to an order of magnitude faster than those baselines. And our approach is more advantageous for hard instances. By hard, I mean instances with more Pareto optimal solutions. And I also show the detailed number of dominance checks required by the algorithm. The main message is that our approach can significantly reduce the number of dominance checks during the search. Okay, then we switch gear to occupancy grid, workspace with obstacles. So as the message is similar, so our approach runs much faster than the baseline. However, I want to point out that if an instance have less than 100 Pareto optimal solution, then as you can see from the figure, our approach is not that advantageous. But also know that for those instances, the solution time by either of the 4 algorithms is less than 0.1 seconds. In other words, the instances are trivial in terms of runtime. Okay, finally, we test in a city-like road network with 3 objectives. The dataset is a public dataset online. We set a runtime limit of 10 minutes. And from the table on the lower right corner, we can see that our approach doubles the success rates. In addition, among instances that are solved by all 4 algorithms, our approach runs up to an order of magnitude faster than the baseline approaches. Okay, so to summarize, in this work, we propose a new approach that generalizes the existing BOA* search to handle an arbitrary number of objectives. And the key point is that we incrementally build balanced binary search trees during the search, which help reduce the number of dominance checks. And consequently, we are able to expedite the existing method for up to an order of magnitude. Our code is available online. And that's the end of my talk. I'm happy to answer your questions. Thank you.